Good evening, all of you. So, can you see my screen? Hello, everyone. Hello. Can someone mute yourself and tell me? Can you see?
Yes, yes,
Okay.
yes.
Yeah. So, can we start now? So, if you have any doubts from the lecture or from any tutorial, from any assignment, you can ask me. So, we today so welcome all of you. So my name is Anil and I am TA of the course Fundamentals of the Semiconductor Devices. So today we will start with the basics of the mobility, why it is so important for the devices and all. So what is mobility and why it is so important? So actually, huh, so mobility is really very important for the like device performances. So how uh, electrons move inside a semiconductor. So if in this case, what you can, okay, huh, I don't know, huh. So in this case, this particular case, when there is no applied field, the electrons move randomly inside a semiconductor. So in this is a like piece of semiconductor, this is a piece of semiconductor, and electrons are moving. Okay, just keep. Mhm. Someone wants to join, so just give me a minute. Okay. So electrons move in random directions. Electrons or holes move in a random direction in a piece of semiconductor when there is no field applied, but at a certain temperature, but at 0 Kelvin, say absolute zero, the electrons are, everything is static, there is no movement of electrons or atoms and in any direction. Okay. So when when we increase the temperature in electrons get sufficient energy from they transit from the valence band to the conduction band, that as we have discussed previously. And from the in the conduction band they have so many empty states, they are free to move in the conduction band. So at they have uh, a sufficient amount of energy, so they can move. But when when we do not apply any electric field, there is no certain motion in a single direction. Okay. So electrons are moving, we know, in a semiconductor, but when we do not apply electric field, there is of no use. Okay. So electron let's say this is an electron, so it is moving in this direction because of the thermal velocity, because of the thermal energy, it is moving this this. But but it is here, it will come at the same place after some time. Or actually we in like quantum mechanics, in quantum we take a ensemble of the electrons. We do not talk about a single electron, but we talk about a collection of the electrons, collection of the particles. We do not talk about a single particle or single, we cannot talk, because there are 10 10 raised to power 10 10 raised to power 15 or so many electrons. Okay. So there are like 10 raised to power 23 Avogadro number of atoms in per centimeter cube. So we cannot talk about a single atom. We always talk about a ensemble of the electrons. Okay, wait. Someone wants to join. Huh. Okay. So so let's take a cross sectional area of this one cross section. So electrons coming in this direction and going in this direction at any point of time is equal when we do not apply electric field. But as soon as we apply the electric field, say electric field in this direction, this is shown electric field in this direction. So what will happen is electron will start the electrons will start moving in the opposite of the electric field. So there will the motion will be random, but there will be a displacement of the electron. There will be a net displacement of electron from this point to this point in certain time. Okay, so electrons are moving, so therefore there is a flow of current. As so this is the drift current. So drift current is that current which is when electrons or holes move under the application of the electric field. Okay, so the movement of charge carriers due to the electric field is known as the drift. Okay, electrons always move opposite to the field and holes move in the direction of the field. So what we can see, as we have seen the conduction, this is the conduction band and this is the valency band EC and EV. Okay, so if there is this gradient in this conduction band, so it represents the electric field. And electric field, so how we can say that what is the direction of the electric field? Okay, someone. Okay, so yes, so electrons move opposite to the direction of the electric field. So if there is a gradient in the conduction band in the band diagram, so electron will move downhill. Electron will always move downhill. So electric field will always be opposite in this direction. Okay, if whenever you find there is a gradient in the conduction band like this, so electric field will be in this direction. Okay, because electron will if we keep an electron here, it will roll down in this direction. Okay, so like this we can find the electric field in any semiconductor from in which we are given with a Venn diagram. Okay, so uh, huh. So all this is about the how electrons move in the conduction band. But as they move electrons move in a semiconductor. So what will happen is they always they like collides with the atoms which are already present in the semiconductor. So electron cannot move directly like this. No, because there are atoms, there are so many atoms, they will definitely collide, and the electrons are also vibrating at their points, at their lattice points. Okay, these atoms are vibrating because of the thermal energy. They can be think of as a like this is an atom, this is an atom, there is a spring kind of thing connecting them. So they will be they will be vibrating like this, or they can be vibrate up and down, or can be of any type. So as electron will move in this direction, they will be colliding with these atoms because of the vibrations. Okay, so this will hamper the movement of the electrons. These collisions will hamper the movement of electrons. So it will decrease the this movement of electrons in any direction along in opposite to the electric field. So this is the concept of the mobility, how it came into the picture. Okay, and this so what I said, these collision of the electrons or holes with the atoms or with anything with the atom, this is known as the scattering. Okay, so how scattering happens? So this is how atoms are vibrating. So this is a, like, pictorially they have shown, someone has shown. So I took all most of these pictures from the Wikipedia or Google Images, and some of the part of this lecture is taken from the Professor Sushovan's lecture. So these are the vibrate. Huh. So these are the vibrating atoms. So as electron is moving, so it will collide here. So it this uh, vibrating these vibrating atoms are hampering the movement of the electrons. Okay, and what is the another thing which is hampering the this ionized impurity? Okay, so how this ionized impurity, so let us say this is the ionized impurity. So can you see this picture, right? So this is the ionized impurity. So if an electron, this is the positive charged nuclei. Okay, so electron is moving in this direction, so from here to here in this direction. So it is not in the vicinity of this electric field or the potential of this positively nuclei, so it will pass through. Okay, so there won't be any effect of this positive nuclei to this electron. So electron or hole, it can be electron or hole, the nuclei can be this charged atom, this ionized impurity that we are doped with the semiconductor, that can be of positive charge or negative charge. Okay, so it can hamper this the charge, the electron or the flow of electron or hole. So but if it is not in the vicinity of the this charge, so it will pass through, there won't be any effect. But what will happen if it is in the vicinity of this is we can say it is the capture cross section that we will come across in this lecture. So if the electron is moving in this direction, which is in the vicinity of this positive charge, this positive charge will attract this electron, and it will move like this. It can move like this, it can move like this, it can move a slow deviation can be there, it can be like this. So this deviation depends on the velocity of this electron or hole. So this deviation will be more if this electron has very less velocity. Okay, less velocity, or we can say less electric field we have applied, then it will be a less velocity. So this electron will deviate more. Okay, if the electron has more velocity, it will deviate less. Okay, this direction. If it greater than that velocity, it will deviate more. So the velocity defines how much deviation will be there. Okay, so like this, the electron, it has shown this electron, this is, so it is going, it may be too fast, so it is not that much affecting by the charge carrier. Okay, so there is and there is no physical contact. Actually, this is not contacting with the nuclei, it is like but the deviation itself is the scattering. So there is no physical contact between this electron and this nuclei or the atom. So actually this atom sets up a potential, so because of that Coulombic force of attraction, so this electron or hole is attracted towards the nuclei. Okay, and huh. So now we can derive the formula for the mobility. Wait a minute, someone wants to enter. Mhm. Yeah, okay. So from here we can derive derive the formula for the mobility. So when how can we derive it? So when we apply an electric field in to a piece of semiconductor, when we apply an electric field to a piece of semiconductor, so what will happen is, okay, this is in this direction. So electric field is in this direction, and electron, let us say this is the electron will move in this direction. So how it will move? It will with a various it will collide with the various nuclei, and it will there will be a certain displacement of the electron. Okay, so here, so velocity, how we define this as this, let us say, suppose this there was an electron, so it moved here and then it collided with a nuclei, and then it moved here. So let us assume that the collision between the the time between the two collisions, the average time between the two collisions is tau. The average time between in the collision time, average collision time is tau. Okay, so and we are also assuming as soon as it collides, it stops. It stops. The velocity is equal to 0 as soon as it collides, and then again it accelerates due to the electric field. Okay, due to the electric field, it again accelerates. So from here we can say velocity is equal to velocity of the electron is equal to acceleration into time. That time tau time, this tau is the average collision time. Okay, so and also acceleration is equal to this what okay, acceleration is equal to this charge into field. Here I am denoting field, electric field. Generally we denote it with E. Here I have shown but E we are denoting with the energy in the conduction band and the, okay, just huh, E we are denoting with the energy, which is conduction band and the valency band, EC and EV. Okay, EC or okay, just a minute. Which is EC and EV. So here we are denoting this field with the F. Okay, divided by m star and tau. So acceleration is nothing but this thing. So when we rearrange this with the velocity is equal to q into tau by m star, and there is this relation comes out, v is equal to mu f. Velocity is directly proportional to the field that is applied. Okay, velocity, this is the okay. So also this velocity is due to the application of the electric field. Therefore we call it as drift velocity. Okay, drift velocity. Okay, so we call it drift velocity. So when we plot this drift velocity, this is the drift velocity in the y-axis and with the electric field. So so this is there is a relationship with this straight line kind of relationship. So okay, so we drift velocity is directly proportional to the electric field, but for a up to a certain certain limit, because velocity cannot go infinity as we apply the electric field. Because why? Because as that cannot be okay. So that we will come in low electric field and high electric field regime. So this is the before the velocity saturation regime. This is we call it a velocity saturation velocity. Okay, velocity saturation, drift velocity saturation actually. Okay, drift velocity saturation. So and from this here we got this mobility. This mobility is equal to q times charge times tau divided by m star, and this m star is not a normal mass. this is this is the effective mass. M star is the effective mass which captures everything inside it, or this Venn diagram, the curvature of the Venn diagram, and the curvature of Venn diagram captures the whole quantum mechanics. Okay, this is because of the curvature of the Venn diagram. Okay, so so therefore we can apply this is why we can apply this classical mechanics equations because of this M star only. Otherwise we couldn't apply, because this M star carries everything inside it. Okay, so this is the relation between this is the relation between the drift velocity and the electric field. So till this point, as we increase electric field, so there will be a limit till where this is in a straight line form, but after that it starts saturating. Okay, so velocity cannot go beyond that, so this is known as the velocity saturation. Okay, so before that it is a low field regime, low field regime, and this is the high field regime. So this why this velocity saturates is because, as we have seen in this one, so so if the electron is moving too fast, it will collide more and more. So there will come a time when this both this velocity and the scattering and we can say the collisions and the velocity, they will compensate each other. How? When they will compensate each other, at that time this velocity saturates, because more is the velocity, more will be the scattering, more will be the collisions, and because of that there will be a scattering. Okay, so that is why there is a velocity saturation. And so so how this is the mobility, the formula for the mobility. Okay, mu. Okay, we can write it here. Someone wants to join, I think. Let me see. Yeah. Someone was asking. Okay. Huh. Okay. So what is the effect of temperature on mobility? As we have seen, if we increase the temperature, there okay, thermal as we increase the temperature is increasing, kBT by q. Okay, kBT by q will increase because it is directly proportional to temperature. Okay, this kBT by q is nothing but is the thermal energy. Okay, thermal energy will increase. Thermal energy will increase, then what will happen? It will increase the velocity of the electron. Okay, velocity of electron will increase. So what will happen is, so as I was showing, so if
Screen is not showing.
huh
Sorry, screen sharing has stopped.
screen sharing stopped. Okay,
Yes.
wait, for how long?
Sir, about one more.
Like, just 1 minute, Anil.
Okay,
Just
just
one.
1 minute. Okay.
Yeah.
Yeah. Huh. Now can you see?
Not yet.
No.
Yeah. Now we can see. Yeah.
Oh, now
we
you can see, right?
Yes. Now we can see.
Okay,
Thank you.
okay. So here I am showing the effect of temperature on the on mobility. Okay, this is the mobility. Okay, mu. Huh. So how the temperature affects the mobility is okay, when we increase the temperature. Okay, if we increase the temperature, so this kBT by q is nothing but the thermal energy. This thermal energy will increase, and so what will happen is the velocity of the electron will also increase. There are two things that will increase: the velocity of the electron will increase, and another thing will increase is the lattice vibrations, atomic vibrations, atomic vibrations both will increase. Okay, so at what will okay, uh, impurity. Okay, so at lower temperatures, at temperature is low T, so there will be velocity will be less, velocity is less. Okay, so what will happen is they so in this case, in this figure, can you see? Hello, anyone asking question? Okay, velocity will be less. So if the velocity is less, more is the scattering that I have shown you. Okay, more is the scattering. Velocity is less, more is the scattering. Here here in this case, as we at lower temperatures, so in this direction this is the temperature. Okay, in this direction this is the temperature. So you can you see this graph, this graph, this thing is because of the impurity scattering increases. Okay, impurity scattering decreases with the increase in temperature because velocity increases. Okay, impurity scattering decreases, then what will happen? Mobility will increase. Okay, this therefore the mobility is increasing. So from the experimental data, it has been plotted with the temperature and mobility. So it came out, it is there is a direct relation, T raised to power 3 by 2. Okay, so at higher temperatures, what will dominate is the lattice scattering. Lattice scattering is because of the atomic vibrations. Atoms are vibrating at their positions. Okay, so they are vibrating, so more will so these atomic vibrations are more, these lattice vibrations are more at the higher temperatures, so these lattice vibrations will dominate the impurity scattering. Okay, so this is the case. So if we so now we can see the what is the effect of doping. So you can easily see that impurity scattering is there. So more is the doping, more there will be more centers of the ionized impurities. The more the centers of the ionized impurities, more will be the scattering. More will be the scattering, then less will be the mobility. Okay, so let us say this is the whole mobility, centimeter square per volt second. Okay, this is the whole mobility, and at lower doping concentrations, it was at this is for constant temperature, which is at 300 Kelvin. We are not changing the temperature. If we change the temperature, there won't be, it won't hold, because other things will come. So at different temperatures, we need to keep the temperature constant when we are measuring the doping effect. Okay, so at 300 Kelvin, till a certain doping, it will be constant. So after that, this scattering, this ionized impurity scattering will dominate. Because of this ionized impurity scattering domination, the mobility will decrease. Okay, the mobility will fall. So, and does anyone have any question in this one? You can ask me till here. I think in the next we will start the charge transport. So how the transportation of charge happens in the semiconductor. So we will see. Okay, so now how there are two things, how charge transportation happens in a semiconductor. One is the because of the diffusion, and another is the drift of the charge carriers. So okay, diffusion happens because of the gradient. There is a concentration gradient. Concentration gradient comes into picture when we dope the semiconductor. So how semiconductors are doped, so you need to understand that thing also, but it is not that much required, but I will tell you how the semiconductors are doped. So let us say this is a piece of semiconductor. So when we dope the semiconductor like with phosphorus or this thing, so we can spread a layer of the phosphorus or something atoms, and we increase the temperature. This phosphorus, the atoms of the phosphorus will diffuse inside. Okay, this will diffuse inside. So this is known as a diffusion process. Diffusion process. There is one more process, that is with the bombarding the ions with a high velocity. Okay, keep, I think. Hmm. Okay, you guys can see my screen, right? Okay, so when we increase the temperature, there is a diffusion of the atoms of the foreign element, so which we want to dope inside a semiconductor. So like the phosphorus will atoms will dope. Okay, so how this happens is, so there is always, most of the times there is a gradient. So how this is kind of like this. This is the concentration in the y-axis, and this is the thickness of the semiconductor, this depth, this thickness. Okay, with thickness, this concentration will decrease. But what will happen if, for a time, so as we increase the time, as we will give more and more time for diffusion, so this graph will shift like this. Okay, so so more so in this case, whole semiconductor will be uniformly doped if we will give more and more time. Okay, so there is a concentration, say 10 raised to power 15 of this atom, 10 raised to power 15. So this much concentration will be doped uh, uh, the whole semiconductor if you give a sufficient time. Okay, so wait for a minute, someone wants to join, I think. Huh. So so okay, now because of this concentration gradient, there is a flow of the charge carriers, because of the as electrons tend to move from the higher concentration regime to the lower concentration regime, so there will be a flow of the electrons or holes in the lower concentration regime, so there will be a flow of current. So let us say this is the graph of the concentration, this is the n, and this is the x direction. So this graph there is like this. So what will happen, this is the high concentration regime, this is the low concentration regime, so electrons will try to move in this direction. Okay, so electrons will try to move in this direction, so there will be a current. So electrons move in this direction, current, this is the flow of electrons, this is this is current which is in the opposite direction to the electrons. Okay, so there will be a current. So and this current is given by the diffusion current, which is known as the diffusion current, not a drift current. This is the diffusion current. Okay, and also this is because of the p type doping. Okay, so holes, because at this point the concentration is say n1 p1, at this point say the concentration is p2, so p1 is greater than p2, so holes will move in this direction, and current will also be in the direction of the holes. Okay, so in holes will flow in this direction, and because of this there is a diffusion of holes, and that will be a diffusion current jp. Okay, and here it is jn because of that. So wait, okay. Okay, someone wanted to join. Actually, I cannot see your messages. You just whenever you want to ask question, you just unmute yourself and ask. Okay, so I cannot see your any messages. Okay, so so because of this, there is a diffusion of the electrons. So this, how this diffusion of electrons will what are the parameters this diffusion current will depend on. So this diffusion current will depend on the concentration gradient. This is the concentration gradient, or say this is the slope of the concentration gradient. So this jn is directly proportional to the this dn by dx. Okay, so electron the charge on the electron should be there, and this is jn is given by jn diffusion is given by this one. So we can derive that, that is the derivation is too simple, but I am not going to derive that the this equation jn diffusion. And the same, in the same way we can say this diffusion of the whole diffusion current is given by the minus e dp by dx. Okay, this dp is nothing but the diffusion coefficient of holes, and this is the dn is the diffusion coefficient of the electrons. So the total diffusion current in any semiconductor, there are electrons and holes. Okay, so if the semiconductor is n type doped and p type doped, okay, there can be doping of the semiconductor. A semiconductor can be doped with p type as well as n type, like pn junction is formed like this only. Okay, so how, so this total diffusion current will be because of the electron movement and as well as the hole movement. So the current given by the electron movement is this one, with e, when we take out the e common out, and the whole current is given by this one. So the sum of this whole current and the electron current is total is the total j diffusion current. Okay, so it is given by this equation. Okay, so if you have any doubt, you can ask here how. Okay, so and another thing is the drift current is because of the application of the electric field to any semiconductor. Okay, if there is no electric field, this electric field can be internal or can be outer, can be from the external. So when we can give from a battery, or it can be due to the built-in electric field which is in the pn junction. Okay, pn junction, because of the band bending, there is an built-in electric field at the interface. Okay, so there is a drift of the electrons and holes at that junction. So that is the drift current, not the diffusion current. And the diffusion current is because of the because of the concentration gradient that we have seen. Okay, so due to the difference in the concentration. And a perfect example of this drift current is when a fan pushes in air. Okay, so you can see you can that you can assume that there is a source of the electrons which are being pushed. Okay, and which are being pushed, this source, this fan is nothing but the electric field. Okay, so fan is pushing the air, and the smell of the perfume when we just anyone comes from at, you can just spray a perfume at the corner and you can smell it everywhere. So which is because of the concentration gradient of that chemical which is present there and not here. Okay, so it will move from the higher concentration to the lower concentration. Okay, so this drift current j is given by j so jn, we can say jn and jp both are, there are two currents, because of one is for the holes and one is for the electrons, which is given by e into n mu n into electric field. Electric field is f, we are denoting it with F. You can see my screen, right? I think. Okay.
Yes, yes.
Okay. Okay. So this is given by E into n mu n F. This is the field, nothing field. So and whole current is given by E minus of E actually, P. Actually minus we can, if we are placing Q here, then we put the E negative of the charge, uh, because if Q and electron charge is Q, uh, is equal to 1.6 E, 1.6 into 10 raised to power minus 16 minus 19, okay, into 10 raised to power minus 19. So electron charge is negative and whole charge is positive, so it we are taking it as E only, okay. So this is given by okay, E into P mu P and F. These mu n and mu p are nothing but the whole mobility. This mu n is the electron mobility, and this is the whole mobility, okay, whole mobility inside a semiconductor, okay. So this the total drift current is given by the electron mobility plus the electron current plus the whole current. This is the electron current and this is the whole current, okay. This is the electron current and this is the whole current, and diffusion current is given by this equation, total diffusion current. So when if we want to find a total current in a semiconductor, so it will, and we are also applying an external electric field, so there will be due to the concentration gradient as well as the application of the electric field. So total current will be, because of the application of the electric field is the J drift, and because of the concentration gradient it will be the J diffusion. So total current inside a semiconductor is given by drift current plus diffusion current, okay. So this total current, then we just put these equation in this one, we just substitute this J drift and J diffusion, you will get a total current inside a semiconductor. So these n, mu n, p, mu p, and these are nothing but we have already calculated these things in previous lectures. This n is nothing but the that we have calculated the concentration of the electron, concentration of hole inside a semiconductor, okay. So concentration of electrons in the conduction band, these the electrons in the conduction band are free to move because there are abundance of the of the of of the of empty states, okay. Electrons can move, they are really they are very less gap, there is very less gap in between them, so electrons can easily transit from one state to the other state, okay. They are too dense in the conduction band, so electron can move easily. So this n is nothing but the concentration of the electrons that we have calculated, and this p is nothing but the concentration of holes in the valency band that we have already calculated, okay. So from this we can calculate this J drift current. So that's why we were calculating the electron concentration and hole concentration in the previous lectures, okay. So that's why the Fermi level is so much important to understand the basics of the semiconductor devices, okay. So in this diffusion current there will be a very great role of the Fermi level, because the concentration of the electrons the concentration of the electrons and the holes, the Fermi level moves according to that only, how this concentration of the electrons and holes vary in a semiconductor with the x direction or y direction or g direction, whatever, okay. So now we come on a next thing, which is the Einstein relation. So in Einstein relation, so Okay, so in Einstein relation is derived when J drift is equal to diffusion. When okay, someone wants to join the lecture, maybe. Okay, you can see my screen, right? Okay, with hmm. Yes. Huh. And the Einstein relations is derived using when a semiconductor is in equilibrium. Equilibrium. Okay. Equilibrium means when we are not shining any light, we are not giving any external force like electric field. We are not giving any external electric field or anything. So this is the condition of the electron, the equilibrium at a particular temperature. Okay, we are not even changing the temperature. If we change the temperature, the what will happen is the number of electrons and holes in the conduction and the valency band will change. So we are at equilibrium at a constant temperature. We are not changing the temperature. So if this is the concentration of the dopant atom, okay, or we can say nd donor is the n type semiconductor. Let us assume this is given as a n type semiconductor. Okay, n type. So this is the concentration of holes, concentration of electrons, which is varying with the x, varying with in the direction x. Okay, so how this Venn diagram will look like is, because as we are in equilibrium, so there is no flow of current. So if there is no flow of current, what will happen is the Fermi level will be constant. There won't be any change in there won't be any gradient in the Fermi level. But as we are increasing, as we there is a concentration gradient, accordingly conduction band and valence band has to adjust. Okay, so at this point concentration is high, so the Fermi level should be more closer to the conduction band, so that there will be more probability of the finding the electrons in the conduction band. Okay, so this as the this concentration of the dopant is high at this point, so therefore this conduction band is this Fermi level is more closer to the conduction band. As this concentration is decreases, this conduction band moves far from the this moves far from the this Fermi level, because this Fermi level should be constant because there is no flow of the current. Okay, so and also this conduction band and valence band should follow, because there is okay, we are not changing the band gap. Band gap remains constant. So okay, because of this concentration gradient, there is a change, there is a slope in the in this what to say this conduction band and the valency band. So there must be a field. Okay, so there must be a field, so the field will be in this direction. Okay, there must be a field, this field must be in this direction. Okay, because of this field there will be a drift of electrons, because okay, drift comes into picture when there is a field, and we can clearly see from this diagram, Venn diagram, there is field. So there is a drift of electrons in this direction, in the negative x direction. Okay, in the negative x direction, if there is a drift of electrons in the negative x direction, there will be current in the positive x direction. Okay, this is the drift current. Okay, drift current is in the positive x direction. Okay, so this is the drift current. So and another thing is the diffusion current. how the diffusion is because of the concentration of the electrons will move from the higher concentration regime to the lower concentration regime. So at this point, let us say this is x is equal to 0, at from x is equal to 0 to x is equal to 1, x1, so electrons move in this direction. Opposite to the drift, electrons are moving in this direction, so there is diffusion of the electrons. Okay, diffusion of electrons, so the current will be opposite to the diffusion of electrons. So this is the direction of the J diffusion. Okay, J diffusion. Okay, J diffusion is in the negative x direction. So there is a J diffusion current, drift current in the positive x direction, and J diffusion is in the negative x direction. So they will balance out at equilibrium. They should balance out. So this is the condition of the equilibrium, that there is no flow of electron, there is no flow of current, because of that only this Fermi level is constant. There is no slope in the Fermi level. So what will happen? So if we equate J drift is equal to J diffusion, so in J drift is actually we know. So this there is a how this the electrons n this concentration of the electrons in the semiconductor is varied. Okay, this n is given by nc exponential of ef minus ec kbt, that we have already established this relationship between n and this concentration, and between this Fermi level and this conduction band. Okay, so this n is nothing but a variable with the distance x. So nx, this is the nx is equal to nc into exponential of ef is constant. As ef is constant, there is no change in ef, so ef is not a function of x, but ec, this conduction band and valency band, you can take it as a conduction band or valency band. Conduction band for electrons, because we are dealing with the electrons, and you can take if you want to calculate for the holes, you can take it as ef. It will come as nc into exponential of this evx minus ef instead of ef minus ecx. Okay, that will come as evx minus ef. Okay, so this is depending on the this concentration of electrons is depending on the distance. Okay, so as also we know that this diffusion of the diffusion current is equal to q into dn by dx. Okay, this is the nothing but jn. Okay, this is the diffusion current, and this is the drift current, which is qn nx into nx is because at every point concentration is different, and because of the field, this current is the drift current, J drift, which is because of the field, which is the internal field. This is not external field, which is the internal field. Because of the concentration gradient, this field has been created, because at one place there are more electrons, at another place there are less electrons. Because of that, there is a field. Okay, that field is in this direction, from positive to negative. Okay, so now we will calculate this dn by dx from this formula. So nx, as nx is depending, so from here we can calculate dn by dx. Okay, as we differentiate once, so dn by dx is equal to this relationship comes. Dn by dx is equal to nx okay, I might have nc. Actually, I'm really sorry, I made a mistake. This is nc. this is NC. Okay, so this is NC. Huh. Okay, this is NC into NC into exponential of this is minus 1 by kBt. So I think you all know the differentiation. So how to differentiate an exponential? So this is the differentiation. So this d of ECX by dx is nothing but the chain rule of the differentiation. Okay, so this relationship established, and so we will put this back into the above equation, so we will get this relationship. Okay, so now when we equate this diffusion current and the drift current, we will get this dN by dx is equal to this thing. So okay, this EC will cancel out, so this minus will cancel out, and okay, this nx will go, so this there will be this relationship dn okay, this q no, okay, I made a small mistake actually. This q will cancel out here only, this q won't come. Okay, this q won't come. Okay, this q won't come. So finally what will this is the final result that we will get, dn by mu n is equal to kBt by q. Okay, this is the this is known as the Einstein's relationship. Okay, Einstein's relation. So okay, so this is we have assumed our semiconductor is n type. When we the flow process is the same when you calculate the for when this semiconductor is of p type. So what will happen? So it will come out to be dp by mu p is equal to kBt by q. Okay, so it will come out like this. So this is the Einstein relation. Okay, so does anyone have doubt in this till here? So because now we have established the relations that we have seen the total current inside a semiconductor, which is nothing but the total J drift plus diffusion current, drift current plus the diffusion current, and we have established the equations for the drift current as well as the diffusion current, and we have added to get the total current. And these equations are very important to understand the current, understand the basics of the semiconductor, like all the devices whichever device you will work on. So these are the basic equations that will hold. Okay, so and now we can come to the recombination part. So how this charge is recombined, why the charge is recombined? So actually let me first tell you about the what is recombination actually. So okay, you guys can see my screen, right? So if you won't see, just let me know. Okay, so how what is the recombination and what is the generation of the charges? So let us see. So this is the conduction band and this is the valency band, this is the EC and this is EV. Okay, so when we shine light or we increase the temperature, we keep this end hot or this end cold, so there will be more generation of the electrons here and electron hole pairs. So electron in a semiconductor, so we are assuming that this is an intrinsic semiconductor. Okay, intrinsic, we are not introducing any dopants in this one, intrinsic semiconductor. Okay, so what will happen is if we make this end hot or this end cold, what will there will be more electron and hole pairs here and well less here. So there will be a movement of electrons as well as holes in this direction. So these are the things. And another thing, how so electrons and holes, why? Because there is a more thermal energy here. Okay, electrons and holes are generating because of the thermal energy. So let us suppose this is the, okay, I have, okay, just assume that it is straight, not not there is no gradient in the in the AC and EV. So this is EC, this is EV. So if I am shining a light on this semiconductor, this is the EG. Okay, easy. So band gap. So if I am shining a light in this semiconductor, what will happen is, so it will excite an electron from the conduction, from the valency band to the conduction band. It will give this energy, the photon energy h nu, to the electron, and this electron will take this energy, photon energy, from this light, and it will jump from the valency band to the conduction band. So h nu, this h nu should be greater than the Eg. Okay, the band gap energy, the band gap. Okay, if it will be less, there is no sufficient energy for the electron to reach to the conduction band. Okay, so there won't be any excitation, we call it excitation of the electrons from the conduction, from the valency band to the conduction band. So there won't be any excitation of the electrons. Okay, so there is no generation, we call it a generation. Okay, generation of electron hole pairs. So there from this, for intrinsic, or whenever we are giving an external for intrinsic, when we are giving the extra energy from the outside, so there will be a generation of electrons as well as the holes. So we call it electron hole pairs. Okay, they are always generated in a pair. So electrons will go to the conduction band. So this is generation. So when actually what happens, so we cannot make it like we are giving energy, we are shining light over the semiconductor, and it is electrons are going up and up. So what will happen is there is more of the crowd of the electrons here, and less number of there will be more crowded of holes here. So this cannot happen that all the electrons from the valency band to the can jump to the conduction band. Okay, so so as these electrons can go from the valency band to the conduction band, so like this electrons can come from the conduction band to the valency band. Okay, and this is the easy process, because they know there is no need of the energy that they need to consume, but they will lose the energy. Okay, so this is like if you are throwing a stone from a building, so you just leave it from there. So this is like this is the top of the building, so the electrons will come down easily. But from when you are throwing a stone from the ground floor to the top floor, so you need to give energy a lot. Okay, so if you do not have that much energy of the band gap, so that stone cannot reach there. Okay, if the energy is more, so if stone is going up and up, so it will reach to the conduction band. If it is going up, still will be in the conduction band. Actually there are so many energy states. Okay, so it will go on the above energy state, and it will lose. So okay, this is the conduction band, this is the valency band. So there are so many energy states. Okay, so many energy states. Electron, if the energy of the electron is more than the Eg, okay, electron will go at this energy state, and it will transit to the this lowest most energy state. So why it will come in the lowest most energy? Because the transition time from this to this is in the range of 10 raised to power minus 11 seconds. Okay, and the transition time from electron for falling from this conduction band, edge of the conduction band, to this so from the excited state to this state, so it is in the 10 raised to power minus 9 seconds. Okay, so this process of electrons coming the above states to the bottom of the conduction band, it is like high, too fast. It is 100 times faster or more, 100 or more times faster, so it will come. So there will be a this is an extra thing, so you can just just for your knowledge. Okay, so so there will be will be generation of the electrons and Hall pairs, and electron will jump from here to here, it will release energy. Okay, that energy can be of the form of light. Okay, light, or can be form of the heat. This electron, while coming from this from the conduction band to the valency band, or from to the traps, so that we will see to the traps, so it will emit light. It will only so when it is emitting light, we call it radiative recombination. So because here it is recombining, this electron in the conduction band is recombining with the hole in the valency band. Positive and negative charges are combining. So okay, negative and negative, so electron is falling from the valency, from the conduction band. So we call it as radiative recombination. Okay, so and if it is coming like from the traps, or it is giving away energy as heat or as phonons. Okay, this we call it this phonon energy. So it is not radiating any light, so we call it non-radiative recombination. Okay, and this is really very important for the device perspective, because for radiative recombination we need in LEDs. In everywhere we don't want this non-radiative recombination. We don't want this non-radiative recombination, because in non-radiative recombination there is loss of energy as a heat. We don't want our energy to be lost as a heat. This is like of no use. Okay, radiative energy we can use for the LEDs are we can take it as a light. So in LEDs there is a radiative recombination. We prefer our semiconductor should be light, luminescent. We say there is a radiative recombination. Okay. So but in okay. So but there is not always this intrinsic semiconductor. This is the intrinsic semiconductor. So theoretically there are no energy states in between. This is the energy band gap, this is the conduction band, and this is the valency band. There in between these two there is no, in the band gap there is no energy, there is no energy state. But because of the defects inside a semiconductor, because of the like silicon is one silicon atom is missing at its from its lattice point, what will happen is there is a creation of the energy level. This is the ET is nothing but the trap state or defect state. Okay, there is a creation of the state in between the band gap. Okay, so when we excite an electron from this, so that electron can come here and can get trapped here. Okay, so there we were supposed to get n number of electrons. Okay, but because of the trapping of the electron, we are getting less than n. Okay, we are getting less than n electrons. So it will decrease the charge. Okay, it will decrease the current, nothing but current in the semiconductor. Okay, so that will affect our device, so we do not want these traps. Okay, something in some devices like memory stores, so we deliberately create this the traps. So as the functioning of the device is different from these devices, for from these FETs or LEDs, solar cells, from these devices the functioning of that memory store is different. Okay, so so we will see how these traps are created, why they are in the middle of the band gap. Okay, not in the middle, not always in the middle. Okay, but they can be at this point, this point, this point. Okay, so how, what we call it, shallow traps and deep traps. Shallow and deep traps. Okay, so what are the shallow traps? Someone wants to join, just give me a minute. Okay. Huh. These, what is meaning of the shallow? Shallow is like if the traps are, if the electron traps. Okay, if this there is a trapping of electron, if the electron traps are near to the conduction band. Okay, very near, not too deep. Okay, not too in this region. Okay, if they are in near to the conduction band, then for the electrons, so they are the shallow traps. Okay, from them electron can get out easily. Okay, but from the deep traps are nothing you can think of as a well. Okay, so this is a well and there is a deep well. Okay, so this is the conduction band and this trap is a this is the trap. So if electron is falling in this one, it is very hard to come out from this one, so we call it as deep traps. But if electron is falling in this one, so it can come out. Okay, if with the application of the electric field, or if we give sufficient energy to climb from this one, whether it is a thermal energy or so this is how we, from the thermal energy, we do the temperature dependence electrical measurements. Okay, from there we just qualitatively or quantitatively we can see whether how much, what is the density of the shallow traps and what is the density of the deep traps. Okay, so this is how we these traps are like these are the shallow traps and here is the deep traps. Okay, so in the next one, okay, how many slides? Okay, two more slides are there, but we need to go long. So okay. Hmm. So in this one, I am showing how these traps are created. So see, this is a silicon lattice. So silicon is connected. It is so three silicon are shown. So one is in the deep depth of this screen. Okay, as it is a tetrahedral structure, so one silicon is in the other direction. Okay, so this at the surface there is a breaking of the bond. Okay, at the surface there is a breaking of the bond, so we call it dangling bond. Because of that, there is no force in this direction. Okay, there is no force in this direction, but this silicon is pulling this in this direction, this silicon is in this direction. Okay, so there is a more force in this direction. Okay, and because of that there is a perturbation in the electron. in the potential. Okay, because of that there is a perturbation in the electron in the potential. So there is a how it is these traps are created in the in between the conduction band and the valency band. It is like this silicon, there is one silicon is here and this is sp3 hybridized. Okay, so there is electron in this one. Okay, so they this when they come I think molecular orbital theory you might have read in the chemistry, or this is just a 12th class uh, chemistry. So in this one, so when they come closer, so two silicon atoms sp3 hybridized, there is a split of the energy levels. This is the sigma and this is sigma star. Okay, so okay, so what happens is when there is a breaking of the bond, so this is the actually the okay, what should I say, this is the conduction band only, this is the valency band only. When there is a breaking of this bond, this is the breaking of the bond, where they will go, this is the energy level that will come. Okay, this is the energy level that is will come. Okay, so that is why the energy levels when there is a single crystalline or this only silicon is there, so the energy levels will be trap states will be created at the middle. Okay, and gallium nitride also, gallium nitride, gallium arsenide, so the traps will be created because this is will be gallium and arsenide will be either up or down, that I don't remember how it will come. So either up or down, so if there is a breaking of bond of the arsenide, so it will go here. If there is a breaking of bond with the nitride, it will go here. So there the trap, these energy states will be created in the in between the conduction band and the valency band. Okay, so these are at the surface, because there is the dangling bonds, because dangling bonds we call it because there is no silicon which can satisfy the force here, which can satisfy, there is no bond which can satisfy this silicon. So there is a inward pull for this silicon. Okay, but this is not only at the surface, but if there is this silicon is missing, say this silicon is missing, any other silicon is missing, that can be in the bulk also. Or if this silicon is in our uh, in our when we dope a semiconductor, this silicon is replaced by phosphorus. Okay, phosphorus for n type, and boron for by boron for p type. Okay, so so this there is a this is how these uh, energy states are created. These energy states are created for p type, for n type here. Okay, for p type here. Okay, this is how they are created, because we are replacing this silicon. Okay, so this is how this as I have shown, I told you that if there is a perfect crystal, there is satisfaction of this silicon by hydrogen. Sometimes we coat, we deposit a very atomic layer of other material to satisfy these silicons. Okay, so there, to reduce the dangling bonds, to reduce the trap density. Okay, trap density, we call it as a surface trap density. Okay, surface trap density. Okay, surface trap density, to reduce the surface trap density we can coat with a foreign material, foreign atomic a single atomic layer of the foreign material. So this is a perfect crystal, where there is no trap states at the surface. Okay, so but in reality we cannot, because wherever the surface ends there is a dangling bond, there are dangling bonds, there is a unsatisfied silicon or any material, gallium nitride or whatever, gallium arsenide, whatever it is, there are surface traps because of the dangling bonds. Okay, so these, they will come in the middle of the uh, of the conduction band and in between the conduction band and the valency band. And if this trap density is too high, that will hamper, hamper our charge transport. Okay, that will kill the device. Definitely it will kill the device. It will there is a concept of Fermi level pinning. Okay, and that we can cover in the next lecture also. So because of these trap states, because if this is a very, the density of the traps is very high, the Fermi level will get pinned over here. It cannot move. How much uh, we give the energy, we apply the voltage. So there is, so it will kill all the electrons. It will take all electrons or the holes. Okay, so this is so because of that. Okay, in the recombination, okay, I haven't included that slide. Okay, uh, huh. Huh. So recombination, okay, uh, if the electron is here, so in this perfect crystal it can go directly. Okay, it can emit light. Okay, but in a real crystal what happens is, the if it if electron is traveling in this direction, it may be captured by these electrons. Or if we want an LED, okay, so these, there will be surface. So I think sir will cover the LED. So in LED part we can understand how there is a potential well, we deliberately create a potential well. Okay, so there will be a these electrons will be here, more and more electrons will be here, and more holes will be here. They recombine to give the energy h nu of light. Okay, light. So it in the from this potential well. So but if there are too much of these surface states in between these two, so this is the potential well, there are so many states, so they will capture the electrons and holes. Okay, so there will be less number of electrons as we assumed there should be, because they were captured already by these trap states. Okay, so there will be a less illumination, so electron and holes will be recombining, but they there will be a less possibility of going through this directly this, because there are other possible ways also through the traps, which are non radiative recombination that we have seen na? Non radiative recombination. These non radiative recombination kill the performance of the LEDs. Okay, so not only LEDs, so if there are surface states at the PN junction, okay, if we are making it a heterojunction structure, so one material and another material, so there are surface states. So if electron is moving in this direction, that will be captured by the surface states at the interface. Okay, so if it will be captured, so there will be a reduction in the current, but we wanted current high. Okay, so it will reduce the current, so which is not desired. So we need to reduce these surface states as much as possible. Hmm. so how what is the, like, how this recombination or these traps are trapping the electrons. So 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 there is a so I have written so many equations. Actually these are taken from the from Professor Sushoban's course. So from his slides I took these equations. So in this one, okay, uh, there if there is an impurity, this impurity, as we have seen, there was a scattering or collision of electrons. So if this is the impurity, and this is uh, the effect of the impurity till here in this radius, okay, in this radius, it the effect of, there is an effect of this positive charge or negative charge. If an electron is moving in this direction, and which is in, which falls in this region, if it is moving, it it is captured, okay. If it is moving in the, and this is the potential well, this potential well is nothing but the trap state, okay. If it is moving in this region, it will be trapped, okay. So what is the like probability of capturing the, of, okay. So uh, yeah, I have added too many things in this one. So if mhm, huh, this is the trap state, okay, let us say this is the ET, trap state, and this is the EC, and this is EV, okay. So what is the probability of finding an electron at ET, at T, and this is the EF? What is the probability of finding the electron? Okay, I haven't okay, leave that, huh. Okay, what is the let me check if I included that slide or not. No, I haven't included that slide, but you can calculate the probability from the from uh, from that we have already introduced recently, that Fermi-Dirac distribution. So we can calculate the probability of finding the electron at ET. So whether this state is empty or filled, we can calculate, okay. So this capture capturing rate, this RCA R cap n is the capturing rate of the electron, okay. This R capturing is the capturing rate of the electron. So it depends on what two things: the velocity of the electron, okay, velocity of the electron, it is moving VTH, ठीक है, VTH, okay. And sigma n, sigma n is nothing, sigma n is nothing but the capture cross section. This is the capture cross section. If it is moving, this is the capture cross section of the, this is denoted by sigma n, okay. This is known as the capture cross section, and okay, it is directly proportional to this sigma n and the number of, okay. So if the number of electrons in the conduction band n is high, so the probability of capturing this falling the of electron from this to this state will be high, okay. From conduction band to the trap state will be high. If then there is more and more electrons in the conduction band, then the probability of falling the electron to the trap state will be high, okay. So this R cap is proportional to the n, okay, which is the number of electrons in the conduction band that we have already calculated, and nt into f 1 minus ft. 1 minus ft is nothing but what is the probability of this state empty, okay. What is the density, okay, and okay, this is 1 minus ft is nothing but this is the probability of finding this state empty, because to fall an electron to an electron from this conduction band or band, this state should be empty. If the state is already filled, the electron cannot be occupied by that state because the state is already filled. So we need this state to be empty. So what is the probability? 1 minus ft. This ft is nothing but this is the Fermi-Dirac distribution. From the Fermi-Dirac distribution we calculated this the probability of this state empty. And what is the density of states? This density of this empty states, what was the total density of state was the nt. Nt is the total density of the of the of trap states. But how many trap states are empty is nt into finding that probability of finding that empty state, 1 minus ft. Okay, this is the this nt into 1 minus ft is density of the empty states. Okay, so this capturing this what to say, capturing rate is this given by this. Okay, I think you got this point. So how this depends on these parameters that I have shown you. So more is the capture cross section, more will be the uh, this capturing rate. So more will be the velocity. So more will be the velocity. So we can say this electron is static, and this capture cross section is moving. Okay, this capture cross section is moving in this direction, and this electron is static. So there will be a more and more electrons will come in the vicinity. Okay, more electrons will come in the vicinity. So vth, so it is so therefore it is directly proportional to the velocity of the electron. Okay, so r emit, okay, emission of is nothing but how okay, how this electron is emitted to the conduction band again. Okay, this emitting is nothing but how this electron is emitting to the conduction band again. So it is directly proportional to the number of filled states. Okay, how many electrons are already filled in the ET. Okay, this is ET. So how many electrons are already filled in this ET? So that will be directly, because more and more electrons are there at the ET. This, there is a band of ET. So more and more states are filled. So there will be more probability of going this to the conduction band. Okay, and ft is the probability of finding the electron at this. This is the ft is nothing but the Fermi-Dirac distribution. Okay, nt is the density of states, ft is the probability of finding the electron, and if we multiply both these, this is the density of the electrons which are occupied at the ET. ET is the trap state. Okay, so more is the density of the electrons, more will be the rate of the emission of the electron to the conduction band. Okay, so and there is a constant. Okay, with proportionality constant. So we will find this proportionality constant. Okay, so and the same thing can be applied for the holes. The difference is that there instead of the empty states, we will be looking for the filled states here. Okay, just vice versa of that, what we have done for the electrons we will do for the holes. That's it. Okay, at equilibrium what will happen is the total capturing of the electron will be equal to the total capturing of the holes. So from there we can calculate the En and Ep, the relationship between the En and Ep. So that is not a part of this course, so we are not calculating that. So we are just trying to make it as simple as possible. Okay, so that will at equilibrium conditions we can find that thing. Okay, at non-equilibrium conditions what happens is, if okay, I will take a new slide also. At non-equilibrium conditions, if this is the conduction band and this is the valency band, so if there are more holes as okay, like we shine just for a fraction of seconds we have shine a light, okay, over this. So what will happen is there will be a more number of electrons delta n is generated and delta p is generated in this delta n is equal to delta p, but they are more, okay, which uh, they uh, they are extra, they are extra that should be in the equilibrium, and at equilibrium it should be n and p, n in the conduction band and p in the valency band. So at equilibrium we know that there is np is equal to ni square. This relation holds every time when the semiconductor is in equilibrium condition, okay. When the semiconductor is in equilibrium condition this holds, but when it is not in equilibrium, if np, because of this delta n is created, delta p is created, n plus delta n into p plus delta p, there are more number of electrons and more number of holes they are created, and it is ni square. It is more, np is greater than ni square. So these extra electrons and extra holes will try to recombine, okay. This a system always wants to go to in the equilibrium, okay. So these extra electrons and holes will try to recombine, so they will recombine. So if this is the condition, this there is a more number of electrons and more number of holes, they will try to recombine. So, and in another case, if somehow what happens, if delta n and delta p, more number of electrons and holes are already recombined, there happens a situation when more and more number of electrons and holes are already recombined. In this case n minus delta n and into p minus delta p will be there, which is less than ni square, okay. So this system again wants to go to the equilibrium. How it will go? So it will generate more number of electrons and holes, okay. So in this case generation will happen, okay, generation. So generation will happen. In this case recombination will happen, okay. So if np, we can call it n to whole n and p, if np, okay, np is greater than ni square, in this case there is a recombination, okay. If np is less than ni square, so then there will be generation, okay. For any device, in any device there will be this condition will always hold, okay. So if this condition arises, so then it will try to go to in the equilibrium condition, okay. Just a minute. Okay, so here we were here, right? So due to charge neutrality, so okay, in this change in electron and change in hole are capture in and are emission, okay. In the conduction band should be, okay, there is this is recombination, r is recombination and g is the generation, okay. So and u is the net rate, okay, net rate. U as r minus g, there is r minus g, recombination minus generation, this is the net rate of recombination. If you call it recombination, can be recombination or generation. If it will if u comes out negative, then it will be generation, because r minus g is there, okay. So this is the net rate. So from by solving these, we put all these, there is a long derivation of this thing that I am not covering in here. So it will come out to be R minus G is equal to sigma. These depend on the cross section, capture cross section of the electron and capture cross section of the hole. Sigma P is capture cross section of the hole, and sigma N is the capture cross section of the hole. Okay, and VTH is the we have assumed that hole mobility and this electron and hole are moving at the same velocity and these things. Okay, this is Pn and Ni square. P is the concentration of holes and N is the concentration of electrons in a semiconductor, and Ni is the intrinsic carrier concentration, and Nt is the trap density. Okay, this is trap density, not the electrons in the trap density. Traps, electrons in the traps is this thing, Nt into Ft. Okay, this is the Nt into Ft. This is the density of electrons in the traps, and Nt is the trap density, not in the this electron traps. Okay, density of electrons in the traps, not this thing. Okay, so this is the this is a bit complicated relationship, but so actually what happens is, so this depends on the this difference Et minus Ei. So what okay, I will add a new slide. Okay, so so okay, so in this one what we were talking about, Et minus Ei. Okay, this is the EC, this is EV, and there is this is ET. Okay, this is EI. Okay, in previous you have seen there is a we have seen there is a difference is given exponentially of the difference between the Et minus Ei. So in that one, so this trap state is far. If the trap state is far from the conduction from this intrinsic Fermi level Ei or Ef, whatever we will see if what we take for intrinsic semiconductor. We are talking all about the intrinsic semiconductor in this case. For doped semiconductor we will take Ef, not Ei. Okay, we will take Ef. So if this is very far from the Ei, intrinsic Fermi level, this trap state, so this is not that much effective. So the trap is not that much effective, and it won't trap the electron that much effective. Okay, so actually it all because the Fermi-Dirac distribution that we have seen. So if we see that Fermi-Dirac distribution in this one, so it goes like this. Okay, so in Fermi-Dirac distribution there is very less overlapping at this point in between the trap density and the Fermi Ft. Okay, this is Ft. Et into Ft is very less. If Et into Ft is very less, that we have seen previously that rate of capturing. So if Et into Ft is very less, this is nothing but to find electron density. Okay, density in the traps. Okay, this is the electron. But if this trap is going closer and closer to the this Fermi level, so there is more overlapping in between the Fermi-Dirac distribution and the trap density. So there will be more and more electrons we can find. So more and more electrons. Where are the electrons coming from? They are coming from the semiconductor only. So so instead of going finding the electrons in the conduction band, we are finding the electrons at the traps. So these traps are consuming our electrons. They are decreasing the charge density of the semiconductor. Okay, they are trapping the charges. So the current J, current density will be lesser in this case. Okay, if Et is near to the Fermi level. Okay, so we don't want this thing. Okay, so this is the is captured by this equation in here. Okay, so for holes and electrons, for holes it is given by this one, and for electrons it is given by this one. Okay, so if we take it for the holes, okay, this is Ei and this is the Et for holes, capturing the holes. Okay, so if it is near to the this Et, it is near to the this what to say, Ei, so there is a more probability of finding the electron at the trap state. Okay, and that also depends on the density of the trap states. Okay, so more is the density, more number of the electrons or more number of the holes, in this case the holes, we can find at the trap states. So that's why it is directly proportional to the N and P here. Okay, so that's why it is directly proportional. So that also depends on the this NT, actually, sorry, NT is the trap density. So that's why it is directly proportional, we can see. Okay, and so another thing is the, okay, we u is equal to is this is depending on the Pn into Ni square, that I already told you. Pn minus Ni square, Pn minus Ni square, Pn should be equal to Ni square. Pn minus Ni square is equal to 0. So there it is in equilibrium. So there won't be electron and hole pair generation. Okay, so means there will be recombination rate will be equal to the generation rate. Okay, so they, in any semiconductor there will be continuously generation of electrons and recombination. When this generation and recombination is equal, so that is the equilibrium condition. Okay, so if carriers are excess, which is saying by this equation, Pn is equal minus Ni square, Pn is greater than Ni square, that we have already seen. Pn Np is greater than Ni square. So there are excess charge carriers in the conduction band and the valency band. So they will recombine, they will tend to recombine because they are excess. Okay, so that can be seen from this equation. So this recombination dominates, that we have already seen. Okay, so if carriers are scarce, so Pn minus Ni square is less than 0. That means Pn is less than Ni square. So there will be generation. So they every system, whichever system you take, that tends to go towards the equilibrium. Okay, so Pn is less than Ni square, then it will try to, the concentration of electrons and holes in the semiconductor, it will try to increase. Okay, if it will try to increase, then there will be generation. Okay, so and this thing we have already seen. These defects are most effective at mid gap. Et is equal to Ei, because at Et is equal to Ei, that we have already seen. Let me clear this thing. Okay, I don't know where it gone. Okay. Okay, let me clear it once. Okay, where? Okay, can we delete it? just a minute. Okay. Hmm. Okay. So what we were talking about? So defects are most effective when at the mid gap. So ET minus EI will be 0. Okay, when ET minus EI will be 0, this will term will go to NI. Okay, uh, okay, this will be 1 raised to power 0 1 n plus ni sigma into n plus ni. Okay, p plus pi. Yes. Hmm. Okay, so when okay, it will be go. So this whole relation will be come out will be reduced to this equation. U is equal to this one. So when Et is equal to Ei, so as we have already discussed, when Et tends towards the Et will come closer to the Ei, there will be a more capture of the electrons and holes at the conduction and the valency band. Capture of electrons in the trap states. Sorry for the issue. And this recombination lifetime tau is the recombination lifetime, and which is given by these two formulas. Okay, so from this was till we have done the discard. Till here we have done what we say, we have done the recombination and how this recombination and is affected by these parameters, velocity and capture cross section and trap density and all these things. So uh, and if anybody has any doubt, they can ask me. Okay, let me check the teams once. Okay. So okay, does anybody have any question? Okay, so anything what we can do now is wait. Okay. 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 Chalo. Okay. thank you, and I will upload this lecture on YouTube. So you can, if you have any doubt, you can ask me in the Teams link and in the chat box, and if you have any doubt, you can write me also. Thank you and have a nice day.